Okay, hello. Excuse me, hello. Hear me in the back okay? Good? All right, let's get started. Welcome to Data 8, lecture number 31. Today we're going to be talking about linear regression, some announcements. So as you know, homework 6 is due Friday at 11:59 p.m. Homework 7 is going to be released today and will be due Tuesday at midnight. Also, if you're listening to this on the webcast, I'm sorry, someone forgot to charge the battery for one of the microphones here. So I have the microphone, and I'm hopefully using my laptop's microphone, so the sound quality won't be as nice. Sorry, webcast viewers. Any questions about due dates or homework? All right. Well, congratulations. We are now it is officially 2 weeks exactly before our final. I hope you guys are very excited. So we'll be covering all of classification next week, and in the week after that, we'll have maybe like 1 or 2 conclusion lectures, and then we'll have review sessions during lecture time, so you guys can prepare for the final. Okay. All right. So if there is one motto in this class, I would say it is this: it is to visualize your data first and then quantify it. So you guys just finished project 2, and in project 2, we asked the question, does the death penalty deter murder? Right? So people who are like proponents or opponents of the death penalty, this was one of the main reasons for arguing for or against it, right? So if the death penalty was a very good deterrent to murder, then people would say, okay, maybe we should put in a death penalty. Otherwise, it doesn't seem like such a good policy after all. Now, normally when we're asking a question like this, especially one of this importance, we like to establish causality, right? We like to be able to say, the death penalty causes murder rates to go up or down, or it doesn't cause it. So to establish causality, as we know, we'd like to perform a randomized controlled experiment where we like assign one group randomly to one control and another group randomly to a treatment. Unfortunately, we can't do that in this case because to do so would require us setting up 2 separate societies, and with one society having death penalty and another one not having death penalty, and they're saying, okay, go murder each other. I don't think that would work out. So we can't get a randomized controlled experiment. Instead, what we can do is we can take 2 groups that look similar apart from the death penalty. So we said, okay, let's compare the US in 1971 versus the US in 1973, and take a look at whether the murder rates increased or decreased in that time frame. We picked those 2 years because in 1971 there was no death penalty, and in 1971 there was a death penalty, and we took out a death penalty within this 2-year time span. Okay, so we took a look at that, and we found that from 1971 to 1973 there were a lot of murder rate increases. So when the death penalty was abolished, murder rates went up. In addition, from 1975 to 1977, when we put back in a death penalty, there were a lot of murder rate decreases, right? So we had some data that suggested that maybe the death penalty was having this causal effect. Okay. Finally, we looked at the entire time span from 1960 and 2003. We noticed that state murder rates increased about as often as it decreased over 2-year time spans. So it looks like here there's nothing. So over a long run, there's nothing that special going on. Right? And so you look at this, you look at these, and you're like, okay, what does this mean? This seems like this statement right here for all the years seems to conflict with the statement over here. And the truth is, so if you look at this data right here from 1960 to 2003, we indeed find that the amount of increases was about the same as the amount of decreases. Right? You guys ran a hypothesis test for that. We found it to be true. But if you were to plot those increases or decreases in murder rate, so here, we see that in 50 states in 42 years, there are only 45 more increases and decreases, which is pretty close to 0 because we have 2,100 possible increases, decreases, combinations. And what we found is, so here is a random, okay? So if the murder rate behaved completely randomly, so it went up half the time, went down half the time, we would notice things like this. So here we see, okay, murder rate goes down a little bit, and then it goes up, and then it goes down, and then it goes up here. But you see how these are kind of like wobbly, and maybe they get like some increase overall at the very end. But overall, these are pretty wobbly because this is completely random. On the other hand, when we plotted what we observed in our data, this is what we got, right? We got a lot of increases here, and then some decreases, some increases, some decreases, right? And this is clearly, right here, what we observed is clearly not random. So the idea here is, okay, if you just ran a hypothesis test, you would probably conclude that overall, like the murder rate increased or decreased at about the same rate. So overall, that is true across like a 65-year period, 63-year period. But if you look at the cumulative difference in number of increases and decreases, you see some very distinct patterns, right? So these distinct patterns were what led us to try to do more analysis. Then at the very end, I showed you this plot right here, which is, here's a death penalty rate for the US, and here is a death penalty rate for Canada. I didn't know Canadians murdered people, but apparently they do. But in fact, they have these at different scale for Canada. So if you noticed here, this is like 6 for the US, 9 for the US. They had to like use 3 for Canada and 1 for Canada. So it turns out that in Canada, people are actually a lot less murderous. In any case, we see here that if you just looked at the US, just look at the US, and you see here that this is where death penalty was abolished. So here, death penalty was there, now it's gone, now we put it back in. We ran a hypothesis test, and we did find that in this time span, the death penalty murder rate went up, and then here the murder rate went down. Looks awfully suspicious. But when we compare Canada, we saw here that here the death penalty in Canada and the Canadian death penalty was completely abolished during this entire time span. Why did we compare US and Canada? Because the US Supreme Court has no jurisdiction in Canada, right? So it's kind of like completely separate societies. And if you recall, our claim at the very beginning was that, okay, if the 2 years, 1971 and 1973, are about the same, if they're the same in all ways except for the death penalty being there or not being there, then we can say that there's a causal link, right? And it seemed like there's no reason for us to believe initially that the years 1971 to 1973 looked that different from each other. But we do find that in that same year, 1971 and 1973, in Canada, the death penalty rate also went up. So it looks like those 2 years, there was something going on there, and it wasn't just a death penalty, right? Even without the death penalty, so here Canada had no death penalty, even without the death penalty, it looks like the murder rates for both countries just went up. And so from this graph right here, we can say, okay, well, it looks like here the death penalty, or the murder rate would have went up with, regardless of whether the death penalty was there or not. It just looked like something else was happening in society. You can speculate as to what that is. People were just feeling more murderous or unhappy about life or what have you. But it looks like because of this, because a Canadian murder rate also went up, we can't say that the death penalty or the death penalty law had any effect on homicide rates, or had a causal effect at least on homicide rates. Okay, so this is an important, so I consider this pretty important because it was a subject of debate for many years. So there are numerous studies published over the course of the last 50 years, people arguing for the death penalty, people arguing against the death penalty, people saying one thing or another, using stats to try to draw their conclusions. And at the end of the day, a lot of people ended up doing what we set out to do in this class, which is a quantified risk before visualizing. And basically, if they had plotted these two things, the plotted the US and plotted Canada side by side, they would have found that, okay, it looks like something else is going on besides the death penalty. Any questions? Okay, so a lot of you look unhappy. I think you might look unhappy because we made you do all that work, and all your hypothesis tests were for naught. So indeed, in this class, we'll teach you a lot of techniques, right? A lot of methods, a lot of tools that you can use to draw conclusions. But it turns out that you still have to, there is still human judgment calls when it comes to drawing conclusions. Nothing in stats is 100% certain, especially not hypothesis tests. So basically, the point of you working through all those exercises was, one, to get you used to doing hypothesis tests, but also to make you think, okay, I know all that work, but at the end, it looked like all my work was invalidated because of this particular plot here. And all that goes to show you should really think about your data, explore different models of the world before you go and do your analysis and draw some conclusions. And hopefully that'll let you avoid circumstances like what we ran into in the past 50 years. Okay. So let's review correlation. If you recall from yesterday, we talked about the correlation coefficient R. This little number here only measures a linear association, and it's based on standard units. So if you remember, we converted both x and y to standard units, multiplied them all together, took the average, that's how we computed R. In particular, the value of R is always between -1 and 1. If it's close to 1, you have a perfect or almost perfect line sloping downward. I guess for you guys it's like sloping downward. And if you have R close to 1, you have a perfect, almost perfect line sloping upward. In between those two bounds, you get like clouds of points. Okay, so here they are. -1 is perfect line sloping up, -1 is sloping down. If R is 0, then we say that the two variables have no linear association. Now, a little bit careful here when R is 0, because R, if you recall, is only measuring a linear association. So we'll see some examples today of when you can have a lot of structure in your data, like your data follows a perfect curve, but your R is 0. It doesn't mean that there's no relationship between your two variables. It just means that there's no linear relationship. So if you recall, the way to calculate R was take x and y in standard units, multiply them all together, take the mean. Okay. And it measures how clustered my scatter plot is around a straight line. That's your from yesterday. Any questions about this? All right, so let's discuss some properties of correlation. So things to remember about the value R. So R is a pure number. It has no units. So if you actually look at the units when you convert things to standard units, you actually notice that when you convert things to standard units and you get a z value of 1 or a z value of -1, that number there actually has no units. So it's just measuring. You can think of it as measuring standard deviations, but if you do a unit cancellation, you get no units, and therefore R also has no units as well. Okay, so it doesn't matter what your data are originally, like in terms of units, R will still be between -1 and 1, and it will not have any units associated with it. That being said, R is not affected by changing units of measurement. Right? So even if I switch, say, from inches to yards or like feet to meters or something like that, my correlation coefficient R will still remain the same value. It measures that linear relationship and not based on the units that the data came in. Okay. In addition, if I flip the x and y axes, R stays the same. Okay. So I'm going to show you some of that. Let's take a look. So today's going to be a little bit different. I'm not going to type as much coding because I just want to show you some behavior. What I'm going to do, I'm just going to run code and then explain it. So if you'd like to go through the code later on and figure out what's happening, you can go ahead and run the code. Otherwise, just follow along. Okay, so here we have hybrid cars, and I took just the SUVs. Okay, so here are just the SUVs as we did yesterday. If you recall, yesterday we looked at the relationship between acceleration and cost of the car. Right? We saw that as a car gets faster and faster at accelerating, it costs more. Okay. I have also here the functions that we defined yesterday. So yesterday was such a fiasco for me that I just wrote it here. I'm pretty sure this works. So I'm just going to run that. So here's a correlation function that actually works, unlike the one I wrote yesterday. So here we have standard units, standardized correlation. We're going to use those to kind of explore some data. Okay. Just know what they do. And if you have trouble remembering how they work, come back to my lecture notes and take a look at how we define those functions. But here you are. So we can look at the correlation between acceleration and the cost. Let's take a look. All right, so we see here that, okay, so the correlation was about 0.5, about half. Okay, so we can see, okay, it looks like the data are kind of cloudy. Like we have some random points here, some random points here. So it's not really, really tight around that straight line. So indeed, that correlation coefficient is 0.5 because the data are not super tight. Okay. But we do see that it's positive because there is like a general positive trend in my data. So there, that's 0.5. Okay, so if I were to take my SUV table, let me just get rid of this. Okay. And I converted all the costs to thousands of dollars, right? So here I'm going to show you that R does not change when I change units. So before, I had just a straight up cost, $36,676. I have 36.676 because I divided all the numbers by 1,000. If I scatter plot all of these numbers, I get kind of the same looking scatter plot, but the y-axis here is changed. Okay. If the y-axis here has changed, it still doesn't affect my correlation. So here I still have about 0.5. Okay, so changing units does not affect R because R measures that tightness of that linear relationship. Okay. In addition, if I switch x and y, so here I'm going to take, so here I did acceleration on the x-axis, cost on the y-axis. I'm going to switch the two. So here I'm going to switch. Here is cost on the x-axis, acceleration on the y-axis, but the correlation is still the same. As long as it's like positive, my R is, and if my data were like perfectly on a line, it doesn't matter what the slope of that line is, as long as that slope of the line is positive, my R is still going to be 1. So R doesn't measure like how the data are sloped, it just measures like how closely tied together the points are around that line. Yes, Kevin?
Would the R be 0 if the points were on a horizontal line?
So indeed, R would be 0 if the points are on a straight horizontal line. And that's because, again, R measures like the correlation between the two variables. So if the points are on a completely straight line like this, what you're essentially saying is, even if I were to switch x variables at random, like even if I were to pick an x variable here and compare it to x variable here, I would not have any idea how y changes, right? So that means that R should be 0, and indeed R is 0 because my slope of that line is not positive or negative. But as soon as I tick up that line a little bit and the line has a positive slope, then R will be back to 1. If I tick it down, R will be back to -1. Good question. Was that your question as well?
Yes.
Yeah. Okay. Yes. Okay. So let's talk about interpreting this R. There's some things that you should be careful of. Okay. First of all is obviously be careful about jumping to conclusions about causality. Even if R is 1, it does not mean that X causes Y. We've seen that all class long when we're talking about hypothesis tests, and it does hold for this case. So even though you might get a perfect correlation, it does not necessarily mean that X causes Y, right? So for example, if you look at, I'm trying to think of an example, days where I drink tea and days that I'm alive, it turns out that I drink tea every day, so my correlation there would be 1, right? But it doesn't mean that I'm alive to drink tea or I drink tea to stay alive, right? It doesn't really work out that way. So even though, so here's the thing, you can actually make predictions, right? So if you were to look at my life and you're like, okay, will Sam drink tea today? The chances is pretty good, right? You can make that prediction. You can make predictions without having causality. But you have to be careful, okay? So even though you can make predictions about it, it doesn't mean that one causes the other. It just means that they're highly correlated or highly associated. Watch out for nonlinearity. So even if our data are curved, you can still get R values of something else, right? You can still get R values of different things, but you have to be careful. Visualize your data first. If your data look linear, then calculate R, because otherwise it doesn't really make a whole lot of sense, and it can actually be very misleading at times. Watch out for outliers. So R is very affected by outliers. It's based on the mean and the standard deviation, which are two statistics that are very affected by outliers. We discussed before how if I took a point and I threw it all the way down the south side, my mean would change by a lot, right? So even one really, really bad outlier can throw off my mean, which means that it can throw off down the line, it can throw off my R as well.
Does that mean for regression lines we should take out the outliers?
Does that mean we should take out the outliers? Now that is a hard question and subject to a lot of debate. Usually the answer is probably no. So generally speaking, it depends on what it is. You have to look at your data and you have to decide for each outlier, like, does this outlier actually look like it was not supposed to happen, or was this actually reflective of something else in my trend? Like, it's hard to know without looking at the data. There are actually like a couple of rocket accidents that happened because they just took out outliers, but it turned out that something was actually broken in the rocket. So you do have to be pretty careful about outliers. Generally speaking, it's not a great idea to just take out outliers at random just because it doesn't make your data look good. Okay. So you do have to be careful about that. Finally, there's this thing called ecological correlations. I'll talk about it and show you a demo of that. So I'll explain it with the demo. So let's take a look at these. So I have here Again, the rule in this class, and the rule especially when it comes to correlation, is to visualize and then quantify. So here I have some set of points. I have 4 sets of points. If I run this, I can look at the mean, the standard deviation, and the correlation for every set of xy points. So I have 4 sets of xy points. I'm going to scroll this up and down. So here, the mean is the same, mean is the same, mean is the same, mean is the same. Standard deviation is also the same, correlation also the same. So from all of these statistics, these data sets look basically the exact same. But they are not the same. I run this, and let's look at how these points look. So this particular data set number 2, looks like this. Data set number 1 looks like that. Right? 1, 2, 3, this one is this data set. So these are all in the line except for this one point. Data set number 4 looks like all the points here, and then 1 point over here. Okay, so very, very, very different looking plots, right? Very different relationships between x and y, but they all can manage to have the same mean on the x, same mean on the y, same standard deviation on the x, same standard deviation on the y, and the same correlation. So you do have to be careful with these things. Always plot first. That's pretty much the rule of thumb. So let's look at some nonlinear data. So here I have some data. This is just y equals x squared. The correlation here is actually 0, but we know that there's a relationship between y and x. If I change x, I can actually predict y. Thinking about my data, then my data have to be on a straight line. Correlation is 0, but there is a relationship between x and y. It's not a linear one. Okay. So here I have a line, a perfect line, which means that my correlation should be 1. Yes, excellent. And indeed, plot that. Perfect line, correlation is 1. I'm going to take that line and add 1 outlier. I'm going to put this here, 1 outlier. Okay, same line with 1 point down here, and now my correlation dropped to 0. Really unfortunate. Now it turns out that this happens because my data set is really small, and also because the numbers here are pretty low. But in general, this is just to show you that 1 outlier can have a pretty big effect on the correlation. I went from 1 to 0. I went from perfectly correlated to completely uncorrelated. Okay, so in general, outliers will give you a bad time. So let's talk about those things called ecological correlation. So here I have SAT scores of states in 2014. Okay, so if you look at here, Alabama, how many people took the test, the average critical reading, math, and writing score, and here's a combined SAT score. Let's sort them to see which states did the best. So here we have North Dakota, who got average of 620 in math, and also average of 612 in critical reading. It turns out that North Dakota scored above everyone else in critical reading. Let's see, critical reading, or close to everyone else. Indeed, it did do better than everyone else. And indeed, almost in writing as well. Only Illinois had a higher writing score. Okay, so let's look at math. So we can take a look at the relationship between critical reading and math for these different states, and we find that, wow, it looks like if you're good at math, you're good at critical reading as well, right? So why bother putting critical reading in the SAT if we know that if you're good at math, you also do good at critical reading? If you look at this correlation is 0.98, which is almost perfect, right? Almost perfect. What is the problem? What is the problem with this? What is the problem about this? So it turns out that these are averages, right? So each state in 2014, we averaged together a lot of individuals. If you average together a lot of individuals, you suddenly can't really draw conclusions about each particular individual. If you looked at just this scatter plot, you would have said, it looks like a student who did really well in critical reading will also do really well in math. When in reality, something else could have happened, right? You could have had one person do really, really well in critical reading, but do horribly in math, or the opposite way around. It's just that when you average them all together for a state, right? You average together all the scores for a state, you get higher, like the averages tend to come together. So you can't use this to make conclusions about individual people because we're not plotting individual people on this plot. So even though North Dakota is like way out here, we can't say much about like whether or not math and critical reading are actually highly correlated for individual students. So let me ask you a question. So we looked at this data, and we did see that North Dakota is really great, right? Really great. What could have made North Dakota so great at all three categories? Talk to your neighbor about it. Is it just because North Dakota kids are smarter, or is something else going on? Try it out.
For one thing, it's North Dakota. That's different from California, where there's a lot more diverse. Like more people, a lot more diverse. It's like more positive as well. It's like I was so close to saying North Korea. I was so close.
All right, any guesses? What do you guys think? What do you guys think? Any guesses for why North Dakota happened to do so well? Sean?
Lower participation rate.
Lower participation rate. Excellent. Any other opinions? Kevin is shocked. Any other opinions? Yeah, Chase?
I mean, I would guess that it has something to do with the way the state runs the educational system.
Sure. So something about the way the schools, or maybe the schools there are like particularly like geared towards the SAT or something else is happening. Yeah, that's also valid. Hard to know for certain, and maybe it's just random chance, right? So there's always this variable of random chance that maybe North Dakota just happened to score really great that year, but didn't score like, on average score around the national average. Hard to know without some more data. It turns out that in this case, it actually was a participation rate, or we think that it is, because if we look at this, and let's make them go ascending order, what do you notice about these states' participation rate? They're all like at 100, right? So it turns out that in North Dakota, so some states do have different policies when it comes to taking the SAT. It looks like in Washington, D.C., Idaho, and Delaware, they make everyone take the SAT. If everyone takes the SAT, it turns out that generally speaking, you'll get like people who do really well and people who do pretty poorly. In North Dakota, on the other hand, only 2% of people took the SAT. And those 2% tend to do pretty well. So that participation rating. Cool. So let's take attendance. And go for it. I think I got like 30 more seconds. Okay, let's talk about prediction or linear regression. Now it turns out that if you'll walk back with me all the way to like the second week of class, we actually had a prediction example. So if you remember, we looked at Galton's data. So Sir Francis Galton was a scientist way back when in Darwin's age, and he wanted to look at whether or not you could predict the child's height based on the parent's height. Okay. If you recall, we looked at like the parents' heights and we computed this mid-parent score, which is roughly the average of the two parents' heights. So here we have the data that he collected, which was the average height of the two parents and the child's height. Okay. Let's draw them on a scatter plot. And we can see that looks like, okay, if my mid-parent height is about 72, I can look at this strip here and predict that my child's height is about like maybe around like 60, 70, 65, somewhere around there, right? So what he did was he collected this data and he said, okay, based on my data, can I predict the child heights based on the average of my two parents' heights? It looks like here we have a positive trend, right? So as a mid-parent height goes up, that child height also goes up as well in general. We have some really crazy outliers like this guy right here who is like, what is that, like 8 inches taller than his average parent. We have some people out here who had really tall parents but not that tall kids. So we have some data here. Now, what we did was we said, okay, if I want to predict the average height for a child who has parents that are an average of 68 inches, what I'm going to do is take a little slice of points here and take the average y value of those points, and that will be my prediction for the child's height, right? It kind of makes sense intuitively, right? So if I look at the points, I should expect that that the child height here, I can expect that the child's height is about 66 if my parent's height is 68. That's what we did like way back when. So let me run through that code again. So here, the way we do it is we take all the points in between these two markers, which I've done here, in between those two markers, and then take the average. And I get the average child height is probably around like 66. So we wrote a function, if you recall, when we're talking about working with apply, so table.apply. So we can make some predictions. Here's prediction for 68, prediction for 74. And what we did was we used apply to make predictions for every single x value in our table. So it's going to chug along, predict a bunch of points. And if I plot them on a scatter plot, what we see here is, here are our predictions, just based on like the average y value of whatever points are close to the x value. So we can see here, okay, it looks like most of these points fall through the middle of my blue points here. Okay, and this is our first kind of take at prediction. And intuitively it makes sense, and in practice it turns out that it works pretty well. And we give a name to this sort of method. So what we do is we can use a correlation to actually construct a line that doesn't like wobble up and down like this, but goes through most of the points anyway. So our goal here is get a prediction line that doesn't wobble up and down so much, just make it like one straight line, because this is like too much trouble to compute. Okay, so the way we can do that is, what I've done here is I've taken my heights and I've converted to standard units. So we see here 0 on the x-axis, 0 on the y-axis. Both x and y values are converted to standard units, as we've seen before. Red line, I've drawn a line with slope equal to 1. Okay. On this green line, I've just drawn the green line at a particular x value that I want to predict. So here I want to predict what the child height should be if my mid-parent height in standard units is about 2.5. So here's like 2.5. Look at these points here. Does this red line look like it's a good prediction line for my points? Probably not, right? Because if we look at these points here, it looks like if my parent's height is about 2.5 in standard units, I should predict my child's height is about maybe 1-ish, right? Probably like 1 if I look at the average here. So it looks like this red line is not what I want. But it turns out that if I draw the same plot and draw the line with the slope of the correlation, so I computed R and drew the line with slope R, it turns out that this blue line here actually does go through the middle of these points here. Okay, so we notice, so it turns out that that correlation, if you take that correlation and use it as a slope, when the points are in standard units, you get a pretty good prediction line. A line that goes through the middle of most of these points. So if we look at this slice right here, maybe like a -2, the blue line does indeed go through like the middle of those points. Look at the slice at -1, the middle line, the blue line does go indeed through most of the points. So that blue line is what we call a regression line, and it tends to go through the middle of our points for every single y value. And it's more convenient than what we've done here, because this one right here is kind of wobbly. This one right here is like a nice smooth line. Okay, so take a look. I think okay. So it turns out that, so you notice something interesting, right? I use a value of R. And what we get is, I'm going to turn off attendance. Any objections? Excellent. All right. So what we did was we said, okay, beginning of class, we can look at a graph of averages, right? So look at the XY pairs. Take for every single X value some slice of points around the X value and take the average Y value, right? So that means that for every X value, we get one Y value as a prediction. And if our X and Y values are linear, so if the X and Y pairs kind of have a linear trend, then my graph of averages will tend to fall onto my regression line. Okay. If my data are curved, then my graph of averages will fall into like that curve that the data are on. But if they're linear, then they'll tend to fall specifically on the regression line, which we define as. So what we're going to do is take X and Y, convert to standard units. And what we're going to do is take a look at this line, which is the line that I drew in blue, right? Take my R, use it as a slope for my X. If they're both in standard units, this is my regression line. Y in standard units equals R times X in standard units. Now look at the interesting conclusions we can draw from here. We notice that R is always between -1 and 1, right? What does that say? That means that on average, Y will deviate from 0 less than X deviates from 0. And this is known as the regression to the mean effect. So on average, so it's not saying about individual points, because you can have individual points that like go like really far above or below the line. But it says on average, we draw that line in standard units, the slope will be 1 or -1 or less than that. So even if I get an X value that's really far out, my Y value will be less than the X value. I'll regress. It's called regression to 0, regression to the mean. Okay. All right, so this is a correlation. This is our regression line. And again, it's not true for all points. It's a statement about the average point. The average point will be on this line. Okay, so let's take a look. I have here. So do notice that because R is the same, when I flip X and Y, here I'm going to take the same plot, flip X and Y. So here's a scatter plot. I put, okay, so here's main parent on the X, child on the Y, child on the X, main parent on the Y. But this blue line still goes through the middle of most of my points, right? So if I look here on the x-axis, maybe like 1.5, the blue line does go through the middle of most of these points here. If I look at, say, this group of points at 2.5, it does go through the middle of most of these points here. So if I flip X and Y, correlation is the same. So my regression line actually stays the same as well. Cool. So let's run that. And so we have this line. And what this line is telling us is, if I happen to have X and Y in standard units, I can make predictions, right? So let's take this one up here. Let me erase that. Okay, so here I have this. This line is saying, okay, if you give me an X value of 2.5, I will predict the value, this looks like about 0.8. If you give me the X value -1, I will predict maybe like -0.4, 0.5. So we can get that, and we can get that in standard units. But what we're really interested in is the original data, right? So here we have heights, parents, heights of children. I want to know, like, okay, standard units is good and all, but I want to figure out if my mid-parent height is like 75 inches, my child height should be how many inches? Because that's more useful to us looking at this data. So the way we can do that is we can note this. Let me see. Okay, so what we can do is this. We have here a relation between X and Y in standard units. And we can just convert from standard units back to original units. Okay, so the idea here is X in standard units is what? The original value of X minus the mean divided by standard deviation. So we can plug that back in here. The standard units of Y is Y minus the mean of Y divided by standard units of Y. So we can plug that back in there and substitute in our values and hopefully get back our original value, our original prediction for Y in our original units. So let's see, go. Here we have this equation. It's the same as the one I showed you before. It looks really complicated, but what I've just done here is this used to be Y in standard units equals R times X in standard units. And what I've just done is convert plug in back how to convert them from the original x to standard units. So we can see from here that if we know the average of x, the standard deviation of x, we know the average of y, standard deviation of y, and we know r, then we can say for any given x in original units, I just plug them back in here, solve for y, I can get back y in original units. That's the basic idea. So y in standard units, x in standard units. And what we can also do, is if we like kind of move this, do some algebra here, and move some stuff back over to the right-hand side, we can actually get an original line in original units, y equals slope times x plus intercept, which is in original units and not standard units. Let's take a look. So I have here, I took in both data sets, taking the average and the standard deviation, the average of child height, the standard deviation of the children, and here's the r. This lets us write a function called predict with r. The way we use this function is we pass in a parent height in original units. What it does is it'll convert that parent height to standard units. Once we have it in standard units, the y value in standard units is just r times that. So we do r times the standard units, and then we convert that back to the children, back to the child height. So we have here a function that will do some predictions for me. So it looks like my regression line, given a mid-parent height of 68 inches, will predict that my child is about 66 inches tall. Here I have 74 inches. So do notice that the mean of the children is 66, the mean of the parent is 69. Do notice that the average child height is basically, the predicted child height is less than the parent's height every single time, pretty much. But if we go below the average, you notice that the children's heights that we predict are closer to the average of the parents. Let's try it out. So take that, let's go below the average parent height. So let's go maybe like 60. And here the child's height predicted is a little bit closer to the child's average because of the regression to the mean effect. The slope of that line in standard units is always, pretty much always going to be less than 1, which means that our y prediction values are always closer to the average than the x prediction values. Okay, so here is our original plot. The yellow dots are what we did in class earlier, which was just took the average y value and plotted them. So they're kind of bumpy. Now we have a nice line that goes through most of these yellow dots, but also goes through the middle of most of my points in this cloud. Okay. Finally, I can do that. So this is just, it's actually the same plot. The same plot, but instead of a line, I actually use a line to make predictions for every single value of x. So indeed, these points all follow in a straight line. This is our first example of prediction using correlation and using the tools that we've developed in this class so far. I'll see you guys tomorrow.